In this video, we're going to go through some alternative kinds of calculations, ways that we can actually use osmotic pressure to solve laboratory problems. And one of the things that we can do is we can actually use osmotic pressure to help us to determine molar masses for unknown substances. In particular, substances like biological substances, proteins, enzymes, so on, that have large molar masses, where measuring the significant molar concentrations of them might be difficult to do. Now, the reason why osmotic pressure works in these circumstances is we saw in the previous example, a relatively small molar mass, or excuse me, a relatively small molar concentration, 0.3 molar, was able to produce nearly 8 atmospheres of pressure. So even smaller concentrations would be able to produce something that is measurable that we could detect. And so using incredibly dilute solutions with small amounts of material in them, we can actually find out quite a bit of information. So let's take a look at a couple of examples. In our first example, we've got a 47 milligram sample of a water-soluble non-electrolyte that is isolated from some tree in South Africa. And we dissolve it in enough water to make 2.5 milliliters of solution. We are told the osmotic pressure of the solution is 0.489 atmospheres at 25 degrees Celsius. What is the molar mass of the compound? Well, as with most problems of this kind, it really comes down to definitions. Molar mass can be found by taking the mass of a substance and dividing it by the number of moles of a substance. And that ratio of one substance measurement to another can give us the molar mass for the material. Now we're told we've got a 47 milligram sample. That's our mass of substance. We just need to convert that to grams. What we also need to do is we need to convert into moles of substance. And so that's where our osmotic pressure is going to come in. So our osmotic pressure is going to be equal to I times M times R times T. Now we're told already this is a non-electrolyte, so we know that that means that I is equal to 1. And we can figure out the value of R because we're given an atmospheric pressure, and we have the temperature here. So the only thing that we're missing is the molarity of the substance. If we can find the molarity, we have a volume, we can find the number of moles of our substance that are present. So let's start working on this. 0.489 atmospheres of pressure is equal to 1, the value of I, times M, which we don't know, times R, since we are dealing with atmospheres, our R value is going to be 0.0821 liter atmospheres per mole Kelvin. And our T value, 25 degrees Celsius, is 298 Kelvin. So if we set ourselves up 0.0821 multiplied by 298 times 1, we get 24.5, well, let's keep this unrounded, 24.4658, 24.4658, and that would be liters times atmospheres divided by moles. The Kelvin canceled out when we multiplied the two values together. And that is equal to, and we have that times M, which we still don't know, and that is all equal to the same 0.489 atmospheres. If I divide each side by my 24.4658 liter atmospheres per mole, 24.4658 liter atmospheres per mole, what I get is my atmospheres will cancel. I'll be left with 1 over liters per mole, which, if you remember from your algebra classes, this would end up becoming moles over liters, which is molarity. And that's going to be important for us in that last step. So 0.489 divided by 24.4658, I get a molarity of to 3 significant figures, 0.0200. Moles per liter is equal to M. Now, keeping in mind that it means that we have 0.0200 moles of the solute for every 1 liter of solution. If I multiply that by my 2.5 milliliters, and then multiply that by 1 liter is equal to 1,000 milliliters. What I get, liters cancel out, milliliters cancel out. I'm left with just moles at the end of this process. 0.0200 multiplied by 2.5 divided by 1,000, I get 5.00 times 10 to the negative fifth moles of the substance. Now we come back to the idea of molar mass. I've got 47 milligrams, so molar mass is equal to 47 divided by 1,000 is 0.047 grams of substance divided by 5.00 times 10 to the negative fifth moles of substance. So 0.047 divided by 0.0000500. I get a molar mass here, 940 grams per mole. So the molar mass here is quite significant, but it didn't take much. The molar concentration was incredibly small here, but we were able to determine that whatever this substance is, it's got a pretty heavy molar mass. It's a pretty massive molecule. Let's take a look at another example. An aqueous solution is made by dissolving 11.9 milligrams of a non-electrolytic protein in enough water to make 4.88 milliliters of solution. If osmotic pressure is 523 millimeters of mercury, what is the molar mass? Okay, same kind of problem, same setup. We're going to follow the exact same process. So 523 millimeters of mercury is equal to, again, non-electrolytic, so I is equal to 1 times molarity, which we don't know, times R. Since we're in millimeters of mercury, we're going to use 62.36 liters times millimeters of mercury divided by moles times Kelvin. And we're not told the temperature here, so we'll just assume that is 25 degrees Celsius, which is 298 Kelvin. All right, so let's do some of the calculations here. 62.36 times 298 times 1 gives me 18,583.28. So that's this side of the equation. 18,583.28 liters times millimeters of mercury divided by moles times M, or unknown, is still equal to 523 millimeters of mercury. We do our division here, and we end up getting M is equal to 523 divided by 18583.28. Our molarity here is 0.0281 moles per liter. We're going to do the same calculation with it that we did in the previous. Multiply it by 4.88 milliliters. Multiply it by 1 liter over 1,000 milliliters. And if we do that times 4.88 divided by 1,000, we get 1.37 times 10 to the negative fourth moles of the protein. And so molar mass is equal to 11.9 milligrams, so 0.0119 grams of protein divided by 1.37 times 10 to the negative fourth moles of protein. So let's take that 0.0119 grams divided by 1.37 times 10 to the negative fourth, and we get 86.86, so 86.9 grams per mole, which would be incredibly small for a protein. But that's what the information here gives us. So that's a really good look at osmotic pressure, and this is a very common direction that osmotic pressure goes and things that we can do with it. Don't be surprised if you see a question like this in your homework, on your Chapter 11 quiz, or certainly on that next exam. Until next time, we're going to talk about Henry's Law in our last colligative property video. That'll close out Chapter 11 for us. Have a good day.